Hello everyone, I am Tobias's PhD student, among other things. I'm also in the Polonius working group, and we're working on developing a new version of the Rust borrow checker that addresses some of the shortcomings. And in this talk I'm going to talk about mainly what we're doing and how it's been going, which is essentially poorly because we haven't released it yet, if you have a very binary view. But I'd like to talk a bit about Rust and why I think Rust is so cool. And essentially, so it gives you a lot of fun stuff, but the cool thing is that you can do ownership types in a real world setting. Someone's going to be upset with me for terminology I'm using at some point. But essentially, when I talk about ownership types in the Rust context, this is what we mean. Every value has exactly one owner. When it goes out of scope, it's deallocated. And you can borrow a value to make a reference, but you have to have the only reference if you're doing mutation. This should not really surprise anyone in here, but I keep it around anyway because you might need some background. And so the problem essentially we're looking for is that for every value, this is the problem solved by the borrow checker, is that for every value access, we want to determine, or potential statically, we want to determine that all values that are accessed are still valid, so they're still initialized, that no terms of a loan are violated, so you're not trying to mutate a shared loan, and you're not even having overlapping mutable and shared loans. That's it. And also that your lifetimes are guaranteed to be long enough. I'm going to have a straightforward example of where that isn't the case soon. But essentially, the initialization tracking and the deinitialization tracking isn't very interesting. It's not going to change with Polonius. It's unlikely to change at any point in time because it's essentially as good as it's ever going to get. So what we care about is the reference mechanics. Those are the things that can be improved on. So what the borrow check boils down to is essentially a subtyping check. So essentially what happens is you have a function. In this case, as the name suggests, I'm trying to return something that is on the function stack. That's unsound and not allowed. So it's a straightforward example of something that isn't. But you can still, in Rust, have functions be generic over the lifetimes of something. And a lifetime is an inference variable that captures something about a reference. And that something, what that is, has changed with Polonius, or will change with Polonius. So in this case, we're promising, this function is promising to return something that lives for A, or whatever A might be, and it's a U32 integer. And in this case, that something turns out to be a subtype here, like it's given its own inference variable, and then it's evaluated as a subtyping relationship, which create this outlives relationship that we usually write with a colon, very confusing when you have a quantifier involved. Because that one also comes with a colon. So usually I will be skipping those. But essentially what we're promising is that for any possible values of A, we will be returning something that lives at least as long as that. And in this case, the interpretation of one possible thing we can slot in for A is that something on this stack frame lives for at least as long as A. And then we can put in the counterexample, which is static is usually what we mean by the entire program. It's the largest value you can possibly give a lifetime. So that's a counterexample, and therefore you would get a compiler error. However, if you change this so that you're returning something, the subtyping relationship will be this quantifier is smaller than that quantifier, and that is essentially just identity. So you're returning something that is something, and then it's fine, because that's always true. The crucial thing about this, the analysis in general, is what the heck goes into the lifetime. That's essentially the job of the borrow checker, is to figure out what kinds of things to put in. And I'm being cagey about what I mean by things, because things have changed. So the interpretation in the current version of Rust is that this thing right here is a control flow graph in mere form of a Rust program. It would look like that. It's a bunch of basic blocks. You've seen them in any compiler course. And it's essentially a set of these blocks. So essentially, where can that reference be dereferenced? That's what we mean currently when we talk about these lifetime variables. And with this interpretation, the task of the bar checker is to put program points into those in such a way as to make sure that it doesn't allow anything that is unsafe. This is an example that where this over-approximation was much less sophisticated. So the first version of the bar checker essentially just went looking for the first closing bracket and put everything up until there into the lifetime. So in this case, you would have this hidden lifetime declaration. It would just say this will live for the entire bracket, and now you have an overlapping mutable use and with this read-only view use here. And that's an error. That was improved on in the current non-lexical lifetimes version, so that essentially the bar checker now knows how to put in brackets based on liveness. But this was what you had to do in the early version, where you essentially had to put in the brackets yourself to make it work. With NLL, we'll split this up into basic blocks, and we will use liveness to figure out that, okay, this variable or this reference isn't live anymore, so you're mutating something that can never be seen by anyone, and I see the audience rolling their eyes. Okay, good. It's just James who hates those types. Right. So essentially what the analysis does is it starts by giving every possible reference its own inference variable. And then for every subtyping that happens, relating them to each other in a graph that looks a bit like that. And then, as long as things are live, move the program points backwards through the graph. I will draw the arrows in the other direction from now on. So everything will be moving backwards across the arrows. Very confusing, but that's standard notation in the libraries. But NLL still has a few over-approximations that it does. So in this example, we have, this is one of the canonical ones, we have a loop where we are iterating over some kind of buffer, and we have an early return here from the buffer. And the problem here is when you look at this for a while, so we're assuming that this parse here actually mutates the buffer. And to the current bar checker, liveness isn't enough to figure out that you're either returning early here and you have only one surviving reference, or you're staying in the loop and you have only one surviving reference that you overwrite, which is dead. So due to this situation, you will get an error here. So it will look like this, and you will have the invalidation of the loan, and you would have things flowing from there, and then you will have this error. So you will have this reference here is already barred for use in the return, and you're trying to overwrite it, so you're not allowed to do that. And the problem here is that, and this is why we're doing Polonius. So Polonius does two things. One, it increases the resolution so that we can handle this case where we have a flow-sensitive situation. We'll go into details of that means. But it also changes the interpretation of the inference variables we use. So lifetimes are now defined as a set of loads. So now what goes into the set is a bunch of possible variables that could be put in the reference, as opposed to places where that reference can be live. So that changes the interpretation, and it will probably change how we have to teach this to new users, unfortunately. When I presented this at Eurorust, the keynote for the previous day had introduced a really nice teaching tool for how to think about lifetimes, and I essentially just went out on stage and said, yeah, all of that will have to change. It's no longer valid. But the second thing is that we now allow this graph of outlets relations to be dynamic. So at every program point, in principle, we can change the relationships between these inference variables. And that's a pretty hefty resolution increase. I will be talking a bit about how I think we can pull that off, because it's not obvious that we can. And in fact, that's why it's taken 6 years. So if we go back and we look at the example again, we see that the outlets graph here would be that the values in buff are flowing into temp and then go out through event, and that's why you get the multiple liveness going on here. And everything is live here because we can either stay in the loop or return, and statically you don't know that either of them, that they're mutually exclusive. So what happens with Polonius is that we allow this graph to change dynamically depending on which variable is live. So in addition to having variables propagate differently on liveness, we also have the relations be different depending on liveness. And that's how we get around it. So essentially we bisect this into two cases, depending on where we are in the execution. So either we're in a situation where buff flows back into temp, or we're in a situation where buff flows into the event and gets returned out. We know that both of those can't happen at the same time. And this is still the same type of analysis. We're still doing flow across a graph with a fixed point operation, but the difference is that we allow the graph that we do the flow across to change. So it's a double graph. So now we have something like that. So we can now talk about what goes into the lifetime, and the lifetime is still set, but now it's a set of things that can be referred to as opposed to places where they're live. So this gives us a nice four-field version of various kinds of bar check we could possibly have. So if everything is static and the flow is also static and nothing is flow sensitive, you would get the 2015 version of bar check. If we add liveness to the propagation step, you get non-lexical lifetimes, which is currently in Rust. And if you add flow sensitivity to the building of the graph, you get Polonius, which is fully dynamic. Probably, possibly the most dynamic version you can have without executing the program somehow, or doing some kind of, I don't know, other thing. So Polonius began as during the work on the original non-lexical lifetimes. Essentially, it was discovered and left on the cutting room when they realized that if they implemented the full version of that, they would have a 5,000% regression in performance on many cases. So they just couldn't do it, and they had a couple of months left before the deadline. So Nico Matsakis essentially took the ideas he had and published them as a blog post. There's going to be a lot of blog posts. So that was the first version. It happened in 2018. And he followed up with a bunch of other blog posts that are also about sort of extending on the idea. And then I wrote my master's thesis implementing bits and pieces of that based off of Nico's initial ideas, and that was published in January 2020, but most of the work happened in 2019. So this is essentially just before I started my PhD studies. And then I did other things for a bit. The plan up until recently, and I assume you can see a pattern here, is that Polonius would be in the 2024 edition of Rust. That is not going to happen. We hope to have, by the start of next year, a version on nightly that is usable, but it will probably not be ready for general use. There are multiple reasons for this. One of them is that we had some problems securing funding for everyone and so on. So like most open source work, it's getting people to pay for someone doing the fundamentals is actually not straightforward. Polonius looked a lot like this. So we wrote it in Datalog. I'm going to expand on what that means. Essentially, since it's a fixed point analysis, you can write rules like this. So this is essentially just a set comprehension. You have a bunch of tuples. So at some program point, you have a loan being invalidated. And if it's live, then you have an error. This is the same rule that I think Will showed us previously, but it's in a slightly different version. And in fact, apparently, this is one of the inputs to Will's analysis. So it's just essentially a database join. You have a bunch of tables with identifying stuff. If these two contain this thing, put it in the third table, and that's how you get an error. And you initialize the tables from essentially walking the CFG, the mirror form, and just outputting these tuples. Another version of that is this, which is a slightly longer rule. Why is my build not working? This is, you can still run this as with a Z option Polonius. So if you turn this on, you will get this analysis running. You can do it today. It's in the nightly version of the Rust compiler. But it is very slow in some cases, and I think it's slightly buggy and slightly incomplete in some cases. I said that it was Datalog, and I lied. So essentially what we have we have Datalog at home version. So this was donated by Frank McSherry. So we actually write something that looks a bit like this. These things are a bunch of vectors that contain tuples, and this is a transfer function that copies things. So we write something like that, but you can essentially mechanically look at the rule on the left and produce the rule on the right, and this is the case for all of them, except some of the joints are slightly more difficult to write. But in principle, you could do this mechanically, and in fact, there's a macro that does that. We just don't use it. And the underlying idea, of course, was that the rules would be easy to inspect. They would be mostly almost human readable. It would be separately defined, so it would be nice and easy to test and discuss and so on, and prototype. So it's actually really a bunch of vectors. Yeah, so some of the reasons why we didn't go with the data flow approach is that it turns out that just collecting the inputs is expensive. Going through the CFG and producing all the input facts takes a lot of RAM. And the intermittent computations are also potentially expensive. So you might be materializing a lot of intermediate stuff or even a bunch of inputs that you end up not needing because you don't know if they're going to be used in the analysis, and there's no way to sneakily do things incrementally and so on, because that's not how any of this works. We also kept running into needing stuff that the compiler already has. For example, variable liveness. That's one of the things I did for my master's thesis. It's implementing liveness and drop analysis in Polonius, and that's completely unnecessary, really, because it's already happening in the Rust compiler, and it's needed for other things. So doing it again is sort of slightly meaningless. So the plan is to get Polonius working. And in order to do that, we have a bunch of intermediate steps, of course. So the first one is to separately implement the perspective flip. Take the current non-lexical lifetimes and essentially invert the types of the data structure so that we now look at places instead of program points. And that's essentially mostly done. And it turns out that that is equivalent to what we already have, which is good, because that's what you would expect. We also...
What do you mean by is equivalent?
It computes exactly the same points of liveness for the same references. So if you... Essentially what we did is we ran all the tests that Rusty normally goes through, but we put in a bunch of assertions that says you do both assert that they're actually point for point equal. And then we have a separate thing, which is essentially, so the trait solver can have higher kinded inputs that end up hitting the bar checker, which is kind of annoying. And I'm currently working on moving all of those out and doing separate treatment. I'll be going very briefly into that. And then we want to make sure that we test the same. That's sort of ongoing, but it's going mostly well. The final step of that is to maybe, if this turns out to be tractable in terms of error reporting, remove the two-way path through Rust and just use the equivalent version of Polonius in the current bar checker. So essentially, don't do the extra sensitivity and just use the version that should be equivalent. It turns out that if you start changing things around, error reporting becomes very difficult because there's a lot of kind of hacky code that does that. There's also a separate track to do some formal modeling, what's actually going on. And then finally, the final step is to start doing the actual increase in resolution. And then finally, and that's also ongoing. We have an early prototype in Rémi's branch of this, but I haven't even read the code at this point. So it's very early. But of course, it's the arrows that are difficult here. It's how do we get across it? How do we, because that involves testing and fixing the bugs and getting it actually ready to merge into something. I don't think I will have time to talk that much about how higher kinded concerns, but this is what they look like. This is an actual test case. And what this boils down to is a subtyping that looks like this. So you have an existentially quantified local instance of a lifetime that has to outlive something that is universally quantified. So you have something through the trait solver, you get these quantified types that says this something needs to outlive everything. And that means that it has to outlive static, because the only thing that exists that outlives everything is static. And the way this is encoded is you have in the constraint graph, the variables have universes, which essentially correspond to how deeply quantified they are, how deep in the nesting you are. And previously, this would be handled during constraint propagation. So when you're taking the stuff in B here and moving them into A, then you would just slip in static as well when you detected that this wasn't good. But this meant that the bar checker now needs to have special logic that handles this, which is kind of annoying. So as a pre-processing step, what we do now is we detect the same case, and then we just add an edge to the constraint graph. This means that you can just do regular propagation across the graph to end up with the values. You don't have to have any special handling, and you can even forget that there's a universe there, because you know that you just move things across the arrows. Whoops, sorry to the sound people. So the plan now is to implement the extra logic in a gradual fashion, both gradually implementing everything in actually Rust-C and to incrementally do the analysis. So ideally, because we can't afford to run Polonius everywhere all the time. That would be a waste. For example, every program that now compiles with Rust will compile without Polonius, because otherwise it wouldn't exist. So the idea is to run a multipass analysis where we first try to get it to compile with something even simpler than NLL, and then figure out where we might have errors and somehow reuse that information when we add depth to the analysis, so that we can drive future versions. Because if something compiles with a much simpler version, we know that we're good. It's just when we have an error that might be a false positive that we can go over again and try to figure out, like, if we increase the resolution, can we make the error go away, essentially. And that way we can amortize the more expensive analysis with because most functions are really simple and don't need that. In fact, I've already used some of that technique to enhance some other stuff, but it's going to be recurring. And so currently, my immediate next step when I get back from this conference is to finally land this work in progress pull request that will move the 3 minutes left. Okay. All right, far future. So what we think we'll be doing in the far future is to extend. So this allows us to talk about what goes into references. So now we can actually say things like, this function will always return a reference to that thing, not just something that lives for as long as that thing, but that actual thing. And this increases the since we now have a way to talk about this in the actual program text, essentially, or even the potential, because we can't talk about control for graph points, but we can talk about fields. We can also describe things like internal references in a struct, for example. So we can say something like this tree node has to refer to something for its arena. This roadmap is also laid out in a blog post by Nico. That's the latest published thing we have. And now we have finally arrived at 2003 in Rust. I had to add in the joke for the audience. Thanks for listening. Okay.
Thanks a lot for the great talk and also for all the work on Polonius, which we appreciate. I was wondering about the sets of loans interpretation. So I can see that one needs to understand that this information is much more dynamic in a sense than in the old borrow checker. So we need to embrace this idea that, for example, what are the outlives constraints under the hood, right, are now taking on this dynamic meaning. Do you think this really necessitates understanding that sets of loans are the kind of primitive notion under the hood? Or do you think, I guess I'm trying to understand, when you explained that you should see a lifetime ultimately as some subset of the control flow graph, does this really break now as a way of teaching lifetimes?
I mean, it shouldn't break because it's still, it's a superset, right? We're still going to accept the program that was previously accepted. So if you wrote your program using the previous intuition, this one is also correct. It's just that we kind of slightly changed the interpretation. Now, the real interesting version of that question that I would like to answer
Sure.
is can we use this notion to increase the helpfulness to newbies in compiler errors? That's the really crucial thing, I think. Because if you flip this perspective, maybe you can shake loose a bunch of other things that will help people write correct programs. But I know it should be backwards compatible in every sense, including the human intuition one, which is why this isn't a disaster. I think at this point, changing the semantics of what Rust means that much would be scary. We can't completely invalidate people's intuitions, I think.
Okay, thank
Was
you.
that a response to your question?
Yeah.
I did kind of cheat.
No, I think that makes sense. Thanks.
Yes, my quick question was just clarifying your penultimate slides where you had types dependent on values and other fun things. Is that in Rust now, or will be in Rust in the future, or
Which one?
the stuff that was on your last slide or the previous slide?
Why is this not?
Curly bracket X close curly.
Yes, no, that's not in there.
And dot arena itself, dot arena is not in there.
No.
I mean, it's in Scala, but by definition, everything is in Scala.
Yes. No, it's
I
not there.
get more of a laugh for that.
No, it's not
It's
there,
late.
and it's not going to be there for a good while.
Right, now the nasty question is, we know this is all possible. We know this is all possible because of the ML kit. If you know what the ML kit is?
No.
Well, then say, I don't know what it is. Sorry, I'm vicious and twisted and jet lagged. It's this thing for implementing ML that was started 20 years ago. It's still going now, and it does type inference for the region calculus. And nobody uses it because if you read the book, there's 20 pages on here's the language, and then 150 pages in, and here's how you use 3 separate debugging tools to find out what the fuck is going on. Really, the most difficult bit of using it is because you run your code and then you look at an annotated AST where it has put what effectively I would call ownership or lifetime or region annotations into your code to say where things are. So I guess the question is, and this would be really interesting, and I like where you're going with this staged thing, but it seems like you're saying, okay, we're going to have the simple borrow checker where the ownership, the borrowing is just latent, it's just there, it's licit in the program, and if you want to do something funny, well, you've got to put in extra curly brackets or extra parameters. And then we're going to have the current NNL thing, and if it fails, you then do the second checker. And then the third checker, welcome to Polonius. And we know and we all know what happened to him. Could you see a situation where maybe it's better to think of Polonius as the core to a refactoring engine that gets you from your C code, where you can do anything you like, actually going back to code that you could get through either the NNL checker or even the simpler checker?
If I can see it as a refactoring engine, I haven't tried
I'm not saying it's there now, but I'm just wondering.
No.
Well, I'm really asking two things. One of which is it seems to me you would actually, Polonius is actually computing the information you would need, and then you could do a post pass to basically say, well, what you had you declared this variable here with this lifetime here,
okay.
then it would have gone through without Polonius.
Mm-hmm. So there are no lifetimes you can currently, there's nothing you can currently put into the type checker that will get your thing to compile if it doesn't currently, with or without Polonius. So it's not, you can't write the types you would need to get it to compile. But if we start adding extra type syntax and so on, maybe you could write those types, but you still need Polonius to verify that you didn't lie in your types.
Okay, and the other question is
You started previously by prefixing it being a short question.
the short question was whether the stuff on the slide was work. This was the long question.
Yeah, no, it will not currently work, and right now it's pie in the sky. But it's I think Nico described it as just bike shedding. So you just have to bike shed the syntax for the thing, and then sort of put it in there once we have the analysis. But every time Nico has said this is just X, it's been more than X.
Right. So while Holly is setting up, maybe you can say something about the original promise of Polonius and Polonius was by describing this in Datalog, it looks almost like the 5 rules, and it's very readable, and like, oh shit, 5,000 X slow down on compilation, we can't do that. Are you going to be able to maintain this with a reasonable effort?
I think so, yeah. It shouldn't be that much more complicated than what's currently in there. It's so writing it, yeah. So the other version of that answer is even the Datalog version, once we started optimizing it, came out as something that was completely unreadable.
Right.
So fast, understandable, pick 1 at most. I'm going to unmic myself.